All right, now for our final section, chapter 9, still talking about stress transformation. Now we're going to talk about absolute maximum shear stress, how that varies from our in-plane maximum shear stress that we've been talking about up until now. Okay, so sort of an introduction into this section and the purpose behind it. Okay, so the strength of a lot of ductile materials depend on their ability to resist shear stress. Materials like a lot of different types of steel, aluminum alloys, and in general a lot of different metals are ductile. If you remember back to chapter 3 when we talked about ductile versus brittle materials. So in their case, it becomes important to find the absolute maximum shear stress in the material when it's subjected to a loading, and not just the in-plane shear stress. So we talked a little bit about the general 3D state of stress that materials undergo, and we've represented them at a point on a cube like this. So with an element that has a normal stress and two shear stress components acting on each of its faces, just like this element here. And in the most general sense, in 3D, just like we did for plane stress, we could develop stress transformation equations that can be used to determine the normal and shear stress components, sigma and tau, acting on any skewed plane of the element like this. So instead of cutting a square into a triangle, we're cutting a cube into this 3D shape with triangular faces. This isn't something we're going to do in this class. It is if you take MAE 343, we do 3D stress transformations. But in talking about the absolute maximum shear stress, as we are in this section, we're going to consider that third dimension and this 3D state of stress as it applies to our simplified plane stress that we've been talking about. Okay, so just as we did in 2D, we can also find the unique orientation of an element having only principal stresses on its faces, looking like this. That is, there's no shear on any face, just like in 2D when we talked about when we had principal stresses, we only had normal stresses coming out of each face, no shear. That's when we would be at our furthest right and furthest left points of our 2D Mohr circle. Well, we're going to be able to do the same thing for this case here. So in general, these three principal stresses will have values ordered from most positive to most negative. So taking into account their sign as tensile or compressive. And we'll order those as maximum, intermediate, and minimum principal stresses from most positive to most negative. All right. This general condition, when we have only the principal stresses and one coming out of each face, is called triaxial stress, because there's a normal stress on each of the three axes. While a true 3D stress transformation is beyond the scope of this class, we can still look at the most common case of when we have plane stress and look at it in 3D. So if we consider material that's subjected to just these in-plane stresses, sigma 1 and sigma 2, that's our normal stresses from the previous sections. So no principal stress on the other face, the Z faces, we could say. We can view this 3D element in 2D. So in the YZ, XZ, and XY planes. And then we can use Mohr's circle for all three of the planes to determine the maximum in-plane shear stress for each case. And then from this, determine the absolute maximum shear stress in the material at a given point. So that's what this plot is showing. We have three different circles, one for the XY plane here, and its associated max in-plane shear stress, tau x prime y prime, that's the XY plane. Then one for the YZ plane, that's this one. And then one in the XZ plane, that's this outer one. So basically, the purpose of this section on absolute maximum shear stress is that we're going to find the radius of our largest outer circle when we plot all three principal stresses. So in plane stress, we had sigma 1 and sigma 2, and then our third principal stress is 0. So that's this one here. And we just plot these normal stresses as we would in the previous section. So if our principal stresses are tensile, they're on this side, or we can have them compressive. We'll see that on the next slide as well. So what we're plotting is the projection of this cube in each plane. So this cube, if you were to squash it down this way into the YZ plane, all you would see is sigma 2 on the right and left, over here and over here. If you were to squash the cube into the xz plane, all you would see is sigma 1 on the left and right, here and here, if you squash it that way. And the last plane you would squash it into is the xy plane, where we have our typical sigma 1 and sigma 2. You were to squash it down in the z direction. So the principal stresses for our plane stress projected into 2 dimensions give us these 3 Mohr circles. Okay, so the xy here is sigma 1 and sigma 2 as the 2 endpoints on the circle. The yz is this one here with sigma 2 and 0 coming out of this z face. And then again, our big circle is this xz, where sigma 1 is here, and then our other principal stress is 0. So there to there is our diameter, and then remember our radius of our circle gives us our maximum. So this tau x prime z prime maximum is the maximum in-plane shear stress in the xz plane, but then since it's the biggest circle, thus the biggest radius, and thus the biggest overall maximum in-plane shear stress, that gives us our absolute maximum shear stress. Okay, so that's in one case. So like I said, the maximum in-plane shear stress is just the radius of that individual circle. But if we're looking at this one here, our absolute maximum shear stress, as our textbook will tell you, is sigma 1 over 2, because that's half of this diameter is our radius, this distance here. But that only holds if sigma 1 and sigma 2 are both positive, meaning both tensile. What happens if one of them's tensile, one of them's compressive? Well, here we're going to have sigma 1 tensile, sigma 2 is now compressive, which means that third principal stress, which is 0, right, and in the z direction is 0, changes which of our planes is going to have the absolute maximum shear stress. If sigma 1 and sigma 2 are opposite signs of each other, meaning sigma 1's positive, sigma 2's negative, because sigma 1's always greater than sigma 2, that's going to give us our absolute maximum shear stress in the xy plane now, because that's our largest circle, therefore it has the largest radius and the largest maximum in-plane shear stress. Again, as implied by the term absolute maximum shear stress, that means we're looking for the largest out of the 3 possibilities. So that would be found by sigma 1 minus sigma 2, and sigma 2 is a negative number, so you're subtracting a negative, so you're going to get a larger number than you would sigma 1 minus 0, of course, and divided by 2 to give you that radius. So that's the value here. So that formula doesn't really hold up the way our textbook shows it. So I put on the next slide an adaptation of other textbooks I've used for other classes, where we can give a more general equation that will fit every time, as long as you follow this rule, where you order your 3 principal stresses as shown previously in that first slide, from largest to smallest, and we'll call them sigma maximum, sigma intermediate, and then sigma minimum. Again, that's in order of where they fall on the sigma axis for our Mohr circle, so ordered from most positive to most negative. If both of our original sigma 1s and sigma 2s were positive, then sigma 2 would be our intermediate, and the principal stress on the z-axis, that's 0, would be the minimum. But in the other case, where sigma 2 is negative, sigma 2 would be your sigma minimum, and the one on the z-face that's 0 would be your intermediate. And then not shown here, you could have both of these principal stresses as compressive, which would then make our third stress that's 0 our maximum, because both sigma 1 and sigma 2 would be negative. But if we use this equation here, where we just subtract the largest principal stress minus the smallest principal stress, including our 0, and then divide by 2, that's always going to be our radius of the outer circle, our largest circle, and thus that's always going to be our absolute maximum shear stress, no matter whether your principal stresses are both tensile, both compressive, or one of each. Or as you'll see if you take MAE 343, if you have triaxial stress, actual values for all 3 principal stresses. So that's it for the theory in this section. But now we have one example, and then there's also a worksheet problem to check out. So I'll see you there.